Good morning, everyone, and welcome back for day 2 of the ARCHER2 HPC Carpentry course. Today is going to be a similar day to yesterday, except we will instead be looking at topics related to using the HPC system, and in particular the ARCHER2 system, which we all logged into yesterday. I'm just going to share some content for today. Coming up, cool. So this is the course material. I'll post a link to this in the chat, but it is available as well through the joining instructions and through the course page on the ARCHER2 website. Essentially, the layout is going to be somewhat similar to yesterday. We'll have 3 breaks, sort of a break halfway through the morning, a bit for lunchtime, and a break in the afternoon to kind of mix things up a bit. If you ideally, it would be good to finish a little bit early again today, but we'll see how we go. The exercises are a little bit more challenging than yesterday, a bit more involved, so hopefully we'll see. Again, if you have questions, please drop them in the chat. I will address them as we go through. It's always good to talk about these things when you're still talking about the topic. Otherwise, hope you enjoy today and get as much out of it as you can. All right, let's get after it. So the first session here kind of talks a little bit about why you might want to use a high-performance computing system. And we sort of covered a little bit of this yesterday, but there are some nice kind of examples in here that sort of talk about situations where HPC can really add value to your work and your research. In the first example, a statistics student essentially wants to cross-validate a model, and that means they need to run the model a large number of times. The example here is 1,000 times, but it could regularly be hundreds of thousands or millions of times. In serial mode, that means that the program is running once at a time. So we run one simulation and then a second simulation. It could take maybe 5 minutes to run that simulation. So all of a sudden, if you want to run 1,000 simulations, you need at least 5,000 minutes, because it probably takes a little bit of time between each model restart to run. And if you have 100,000 simulations you need to run, you're talking about 500,000 minutes, which is a significant amount of time on a small little laptop. So what we often do in these situations, and this is called an embarrassingly parallel problem, the fact that each simulation run is a sort of self-contained unit of work, is that we can run all of these jobs, or we can run batches of these jobs in parallel, and that allows us to reduce the time that it takes to run simulations by the number of simultaneous serial jobs we can run, essentially. In another example, a genomics researcher has been using small data sets of sequence data, but they're going to get some new data that is significantly larger than what they're used to. And although the data sets that they originally had were manageable, the new data set is probably going to be something that pushes beyond the limits of their desktop. And in those instances, the program probably needs, more memory or more disk space. And that is something that is often provided by high-performance computing facilities with very large amounts of memory available per machine. In some of those cases, you may also be able to combine the workloads that we saw in the previous example. So you need more memory, and you might be able to parallelize your problem and reduce the time that it takes to calculate. The third example here, this will be close to home for many of you, all doing CFD stuff, but an engineer is using a fluid dynamics package essentially to run a model in parallel. So with CFD, it's basically like a time marching simulation. So you have a model and you are updating the properties of the model as you simulate changes or the differential equation through time. Some applications have been written in such a way that you can essentially break your model up into zones or sub-modules and then distribute those across multiple computers essentially to share the problem around essentially. And this allows you to increase the resolution at which you can model the simulation both spatially and in time. And so that is something that would be doable on a small machine, but would take an enormously large amount of time to complete. So those are three kind of general examples of where HPC systems can really help researchers actually perform their research just physically if they need more memory or storage, or accelerate their research in the sense that you can perform your simulations faster, or you can do more of them in the given amount of time that you have. I am going to skip this break the ice section and keep going, but maybe we'll have a bit of breakout later on in the break, and we can revisit this idea of sharing a bit more about the research that we're going to be doing. Okay, so most people work with this sort of model at the moment. You have some sort of laptop, and you use your laptop to do a lot of standard tasks, surfing the internet, checking and responding to email, writing papers, maybe collating a bit of data, tweaking your models and your programs, and doing, like some sort of limited testing with small data sets or with short sort of simulation runs. The laptop or desktop, it has a monitor and it has a keyboard and a mouse, and it has ways for you to physically interact with it and to tell it what to do. Internally, to sort of do all of the work that you want it to do, there is a central processing unit and some memory attached to that. And those two talk to each other very quickly. It's where all the calculations are done, where the computer processes all of the commands and instructions that you give it. And then the results of that processing are essentially given to an output, and that could be just basically back to disk, or it could be to the display, or it could be across a network essentially to shared storage or a website or anything like that. So this is sort of the model that we're all very familiar with, the things that we do day to day. When things start to take too long for us to solve on our little machines, we can increase the scale at which we do things. And what happens is we will typically outsource the work that we're doing to a remote server, a server that is perhaps on the floor under your desk, or in a cupboard down the hallway, or even in a data center somewhere, in the world, right? So we send our data and our requests for information to be processed or calculated away from our local machine, and then we wait for that information to be returned to us, or the results of that request to be returned to us. These machines are normally noisy, mounted in like rack cabinets, and often they're referred to when they're sort of remote as the cloud. So good examples of this, Office 365 is like a remote processing request that you initiate through your browser. OneDrive is a remote processing request where you send data or retrieve data from a server a long way away. If anyone uses online gaming, then these are remote servers that are basically running the game for you and then rendering it before sending you images that you visualize on your laptop. So the idea here is that these rack-mounted servers and these large compute facilities, they give us a way to push the workload that we might have previously done locally on our laptop, or have been severely limited by the size of our laptop, to a machine that is more capable of handling the things that we require it to do. So you can think of these as sort of like single servers where we are just dispatching what we require to be done to a slightly larger computer somewhere else. In some instances, a single computer isn't even enough, and we have to use multiple computers. And when multiple computers are working together to complete a task, they're often termed like a supercomputer or a cluster. And the computers have special ways of talking to each other and sharing information so that your task can be solved in an efficient and expedited manner. These types of computers, as we saw yesterday, like ARCHER2, are almost exclusively accessed using a command line interface. They have no inputs or outputs in terms of like a mouse or a keyboard or a display. The only way to get access through them so that you can interact with them is through a network by logging in through the shell. When we have a cluster, we tend to term all of the individual compute units, or the computers which have, or the cores that have shared memory. So memory that both that all the CPUs in that computer can access a node. And the distinction here is that we can't physically build, or we can build some very, very large computers which have a huge number of cores and a single bank of memory, but it's generally more cost effective to build a large number of smaller computers which have still a significantly large number of CPUs and a large amount of memory, but then we bank them all up together, we team them up into these clusters, and each one of those individual compute units is called a node. So this is a good question here, and I dropped a few hints when I was sort of explaining some of this, but think about all of the servers that you might use day to day in your life. Not just the high performance computing ones like ARCHER2, but all of the different servers you might access through your laptop, through the internet, through your phone, at your place of work, and so forth. So while you're having a bit of a think about that, if there's any questions regarding the sort of layout of clusters and how they relate to laptops or desktop computers, please drop a question in the question box. All right, so hopefully you came up with a long list of servers that you access. In this example, they talk about checking email. So every time you make a request through your phone or your Outlook or on the internet now, you're basically dispatching a request to a server that looks at a database of messages and sends back the ones that are related to you. Every time you try to reclassify your emails, either as read or you move things to the junk or you delete things, these are requests that you're sending to a server which actually executes the task for you. So that's a pretty good example. Another good one is every time you go to like a website like Google or Bing or whatever search engine you like to use, a computer essentially has to process the request that you type into your search bar and go away and find you all of the related articles. And it's actually quite a large task that necessitates some significant database building. You know, websites like Google are trawling the internet endlessly, rebuilding the connections and the relationships in their database to help you find the most relevant information that they can. If you were to try and do that on your laptop, you would essentially have to trawl or retrawl the internet every time you wanted to update your search. Another one that is probably not super obvious is that when you're communicating with websites, particularly when they're a long way away from you, you have to traverse the internet through a large number of different routing points. And there are computers dedicated to finding the shortest and fastest way for you to get information from different servers. So, you know, the ideas of servers and the ideas of kind of remote information and remote computing are all around us. And even though we somewhat use them without even thinking about it, they are a very important part of how we do things. And stepping up to using HPC or high performance computing facilities is a very logical step when it comes to taking your research to the next level. So in summary, high performance computing typically involves connecting to very large compute systems, which are typically remote from where you are. They allow us to do things that would basically be impossible on slower or smaller systems. And I mean, we sort of covered this yesterday, but the standard way of interacting with them is through a command line interface like Bash, because the computers don't actually physically have any way of inputting information. We're also trying to talk generally to multiple computers at once, so it wouldn't make sense to have a large number of screens or desktops. Cool. Okay, so let's move on to the next section if there aren't any questions. Working on a remote HPC system. We should be able to rush through this pretty quickly, and then we'll have a short break before going on to the section before lunch. So there are a lot of different ways that people describe remote servers and high-performance computing and supercomputing and clusters. You know, a lot of terminology tends to get sort of thrown around, but they can mean different things in different contexts. And the way you tend to talk about something depends primarily on the tasks that you're sort of trying to achieve. An important one to understand is that when people talk about the cloud, they're generally talking about a generic term that refers to computing resources that are provisioned as people need and in a remote sense. So the resources are virtual and managed by a server or a large group of servers somewhere else. Things that fit into that kind of cloud category are like Office 365, for example, online streaming sites like Netflix and so on would sort of fit into that cloud category. You know, the resource is provisioned to you, so a server is sending you the information as you request it. And then when you finish your session, that kind of virtual server that was sending you information is shut down. There's a lot of big cloud providers out there. You're probably aware of like Amazon's AWS or Google's cloud, or Microsoft calls theirs Azure. But they all basically do the same thing. They provide virtual machines which then, on top of their virtualization, provide different types of services to users that users can buy and mix and match to meet, you know, their needs. The nice thing about cloud systems is that it essentially allows companies to avoid having to buy a lot of hardware to support the software end game that they're trying to get to. And all the hardware stuff is managed by the cloud outsourced company that they choose, and they just get sort of the software service. You can get cloud services which provide sort of high performance computing type solutions. But the term HPC tends to refer to a specific kind of standalone resource that is designed for computationally intensive workloads. So CFD is a very good example of something that fits that bill, so computational fluid dynamics. Other things would be like genomics and any kind of differential simulation. So these are things that require very intensive amounts of compute, where you're solving millions or billions of equation calculations every few seconds. The way that we kind of measure the performance of these HPC systems is through their ability to handle large amounts of data, so the volumes of data that they can handle, and or the large number of floating point operations, or flops. And flops is just sort of like a computer or engineering term for how many times you can add, is that right? Multiply floating point numbers together, where a floating point number is just a decimal number, essentially, with a large number of decimal places. Generally, to support this type of work, these HPC systems need to be basically fixed. So whereas you can think of cloud resources as ephemeral, they're sort of created for when they're needed and then destroyed when they're not needed anymore. HPC systems are always on all the time, and when you are running your process, it is running on what we call bare metal. So you are running on the actual CPU of the system rather than a virtualized system. They're also optimized in the sense that all of the computers are kind of co-located to improve the networking efficiency between all of the different nodes that make up the overall system. In a different sense, you might also hear the word cluster, and this tends to refer to HPC resources which are still significant, but on a much smaller scale or moderate scale to larger HPC systems like ARCHER. So we've already been through logging in. Sorry, are there any questions about what an HPC system is? Or any distinctions that people would like to get clarified? Okay. So moving on to logging in. We've already kind of done this. So yesterday we logged on to ARCHER, but you can basically see that when you log into a HPC cluster like ARCHER2, you start off on your local machine, and then we use the SSH client essentially to create a tunnel through the internet or an internal network to the login nodes. So here the blue is the login nodes. And this login node essentially checked our credentials, allowed us to type in our password, and then authenticated us, and opened that shell session which now exists across the internet or network that we're using to access the cluster. In this instance, the login nodes act as like a landing area where every user who first connects to the machine essentially comes in. And then from the login node, you can load data, get your software running, and then dispatch the jobs that you want to run, or the code that you want to run to the actual high performance nodes. So the nodes here are represented in the gray boxes. And these are not accessed directly by the users. We're going to learn today about how we ask the nodes essentially to do work for us by using the scheduling system, and that'll be after the break. Right. I am going to skip through this because we did all this yesterday. So if everyone is able to bring up their shell, and we are going to SSH onto the ARCHER2 system. Wait a second. So remember that to SSH we need to give SSH our correct authentication details. For me, that was in my SSH config folder, ARCHER2 RSA, and my username and the ARCHER2 login address. Then have to enter the passphrase for the RSA key that we created, followed by the password for ARCHER2 itself. And then we can log in. And there's a little bit of information again here when we log in. They tell us which login node we've landed on. So this is login node 4. They're telling us a little bit about the software distribution or the OS distribution we're using. And they also give us some information about the number of CPUs in the memory available on this particular login node. So remember, a node is a self-contained computer that has a number of CPUs that share a bank of memory. In this case, 512 gigabytes of memory, 515 gigabytes of memory. All of the login nodes on ARCHER2, I think, are the same size. We can do, if we lose this information, we can see that we're on login node just from the prompt, or we can also use the command hostname, find out where we are. So in this instance, we return LN04, again, login node 04. Some of you might have landed on different login nodes. It doesn't really matter. You can do and access everything that you need to. The reason there are multiple login nodes is so that we can share the load of what people are trying to do to get their jobs running across multiple computers, and also to offer redundancy. So if something happens to one of the login nodes, the whole system doesn't have to go down to fix that login node. People can reconnect and they'll be redirected to one of the working login nodes whilst another one is repaired or brought back up. We've already talked a little bit about your home directory. So remember yesterday we learned that our home directory is from the root in home and then the project code twice. So each one of these // here represents a new directory, and then our username. If I go up into the project directory here and list everything that's available, you can see that all of you have your own user directory here. And on ARCHER2, the home directory is backed up. So information stored here is backed up. But as a general rule, you should always back up and keep important data or information secure somewhere else off the system. You will have limited allocations based on your project needs on most clusters or high performance systems. and you'll kind of need to manage your data use to stay within those bounds. Are there any questions so far? Okay. So we already touched a little bit on the contents of this section, but essentially, again, think about the individual computers that compose a cluster, and those individual computers are typically called nodes. Although some people might also refer to them as just servers or computers or even machines. On ARCHER2, we simply refer to them as nodes. A lot of the nodes will be similar in the sense that they're exactly the same computer, just repeated many, many times. But not all systems will have or be composed of a completely homogeneous set of nodes, right? We may have different nodes which are sort of specialized to doing different types of tasks. In different systems, they might be called different things. In this instance, for example, we're on a login node, but it might also be called like a head node if there's just one, or a landing pad, or a submit node. There might be nodes that simply manage the job queues, so they're the ones that send tasks out to all of the other nodes. There might be nodes with different amounts of memory or different amounts of CPU, or nodes which have GPUs installed and nodes that don't. So are typically, well, in Archer's case, there are a number of different nodes which are sort of specialized to doing different tasks, and the node is being designed to achieve those particular goals. The head node or login node, where we're currently landed in our shell, is a good place for setting up software. So if you have to do any kind of software compilation, it's a good place for uploading and downloading files, so you can move things to and from the cluster, like your model results and so forth. And you can also run quick tests, so it's okay generally to make sure that things are working with a very basic test. You don't tend to use, well, you shouldn't use login nodes or head nodes for actually running your jobs, and probably get an angry email from the system administrator if you start to do anything too intensive or time consuming on a login node. When there are really large amounts of data that you need to transfer to or from a system, there may also be what are called like dedicated transfer nodes. So these nodes are reserved essentially for communicating information from the shared disk to the external world. But you'll have to check your HPC facilities guides to, or talk to your HPC administrators to find out whether this sort of facility is available and under what circumstances they tend to use it. In a a large HPC facility or in any sort of cluster, the work that we actually want to do will get done on what's called the compute nodes or the worker nodes. And compute nodes, like we said, come in many shapes and sizes, but they're purely dedicated to completing long-running or hard-to-run jobs. So this is where all of the calculations and the hard work is done within the cluster. The reason we don't want to run any of that work on the head node is that we need to reserve that head node for doing all of these sort of administrative and logistic type tasks to set up our problem. And then it keeps, and the head nodes are kind of shared between many, many users. So the compute nodes are there to do the dedicated work. And they are also sort of managed through a system of, like a software system called a scheduler. The scheduler that we're going to learn about in this lesson is called Slurm. And this is the scheduler that ARCHER2 uses. There are a few other different types of scheduler out there. You might have heard of one called PBS or Talk. And there is an older one called the Sun Grid Engine. But Slurm is a pretty common one, and you'll see this one around a lot if you start using HPC systems. So let's jump back to the ARCHER2 shell. You can, Slurm itself comes with a large number of commands that you can execute from the shell. We're going to see a few of them today, but an important one to know is the command sinfo. Sinfo is a command that provides information about what type of nodes are currently available in the system. So when you run sinfo, you essentially get a table which gives you a partition, the availability, the time limits, so how long jobs can run on that particular partition, the number of nodes that fit that partition, and the current state and the names of the nodes associated with it. So you can see there's a large number of nodes currently available in different parts of the system. And they're currently doing different things. So, for example, there are a few different nodes sort of in this drain state. There's a few different nodes that are reserved, so sort of 93 nodes that are reserved. It's currently 5,733 nodes that are allocated. 16 nodes are idle. And we can also see that there's a couple of different nodes here. So the standard nodes are the ones that most people will be using, and of which there are the most number within ARCHER2. But there are also some high memory nodes and some serial nodes down the bottom here. Now you can read this time limit as 1 day essentially, so the maximum job limit on all of these nodes is 1 day. So this would be hours, minutes, and seconds, days out the front. Are there any questions about the nodes here or sinfo? I think if you want to know a bit about the state, I might have to defer to my helper, Kevin. Nope. All right, well, let's go back to the class. And let's talk a little bit about what's actually in a node. So, more or less, a node essentially contains all the same components that you would have in your laptop or desktop computer, but it just has more of them. So there will be a number of CPU cores. So we all have multi-core systems these days. I don't think any of the manufacturers create single-core machines anymore. And those cores have a small amount of instruction memory called a shared cache. So this is where all your compute instructions are basically injected before they're processed by the different cores. And that CPU unit, as it's called, so central processing unit, which contains all the cores, is attached via an interconnect to some memory and also to some local disks. So this will be like a little hard disk in the node itself. The disk that each node has, particularly those on the worker nodes, is reserved for local storage during the time of computation and for system files needed to run the operating system that allows the node to execute programs and to communicate with the rest of the cluster, essentially. There'll also be like network connections from this overall unit to other compute nodes and to shared storage. So this is our sort of network attached storage, or we also referred to it as scratch storage yesterday. There's some exercises here which we might now do. So the first one asks you to explore your computer. So if you exit out from ARCHER2 or open a new shell locally, you can see if you can find out how many cores your machine has. We then want to do the same thing on the login node. And then there's some help here about how to do it for a worker node. So I'll just let you explore these exercises. I'll send you the link here in the chat. And we'll come back in a few minutes when everyone's finished to work through these together. Okay, everyone, hopefully we're all back now, and you've had a bit of a chance to work through these exercises. Probably haven't given you quite enough information to answer all of these, but if you're somewhat familiar with computers, I think you will have been able to get somewhere. There's lots of ways to investigate the number of CPUs on your local machine. There are some commands in the command line which we'll have a look at, but by far the most common one that you'll all be familiar with is to open up the task manager. It'll be different for different systems. I'm on Windows here, so you just sort of right click on the taskbar and bring up the task manager. It's a little bit zoomed out here, but if we go across to performance, we can see that we've got sort of measures for the input and output, all the different types of system that we have on this particular laptop. And if we just go to CPU and we click on that, You get a graph sort of telling you about CPU activity, but you also get a block down here that tells you a little bit about the speed and configuration of your CPU. So remember, a CPU essentially is a single physical chip that can contain a number of cores and a little bit of cache. In fact, there's multiple levels of cache, as you can see here. And the cache is where instructions are essentially stored before they are executed by the different cores. Now, we had a good question from Alex Lawale before about what the difference between sockets, cores, and logical processors is. Well, a socket is the physical socket that the chip goes into. So most laptops and a lot of desktops will just have a single socket on the motherboard where the chip is placed, or the CPU chip is placed. Some server grade boards, and I imagine a lot of the nodes that we run on ARCHER2 are 2-socket, and I think in some cases you can even get more sockets than that. But essentially this allows multiple CPUs to share a large amount of memory. Within each CPU you'll have a number of cores, and the cores are physical basically transistor circuits etched into the silicon that process the instructions that you send, and they're made up of a whole heap of different components that do different types of instructions essentially. So if you've ever heard of sort of x64 or 32-bit or the ARM architecture, this refers to the type of instructions that each of those cores can process, how the core is physically made, essentially. Now, it can be a little bit confusing because the next step here says logical processors, and this is 8, which is obviously double the number of cores. And a lot of manufacturers now have introduced what is called by Intel as hyperthreading. And hyperthreading essentially is a technology that exists within the cores themselves that allows instructions to be taken from the cache and injected as priority into the different cores. So while this laptop that I'm showing you here only has 4 physical cores, it actually has 8 logical processors, so 8 places where instructions can be placed. And some of these processors might be reserved by the operating system essentially to handle critical tasks, so that you get a nice kind of responsive feedback from your operating system, and heavy workloads are kind of interrupted to inject important instructions that would otherwise lock up your machine. On high-performance compute nodes, we don't tend to enable hyperthreading or have a logical number of processors higher than the number of cores, because the types of workload that we're interested in processing are heavy throughput workloads, and they don't benefit from having a large number of interrupts related to things that the system is trying to achieve. So that's true, Kevin, right? We don't do hyperthreading.
It is actually the ARM, so there's 256.
Oh, so you do have. All right. So sorry, I misspoke there. ARCHER2 does have hyperthreading enabled, but there are 256 cores, but only 8 logical processors. Sorry, but 512 logical processors. An important thing to think about this, though, is that having more logical processors doesn't increase the size of or the amount of information that you can process at any given time. So if you're using all 256 cores, and then you try and use another 256 cores worth of information, the workload will essentially be split between the logical processes. So your runtime will be double, right? Because you're increasing the workload beyond the number of actual physical instructions you can process. Hopefully that kind of answers that question for people. There are other ways to get information from the command line. I'm just going to open up another terminal here. So this is on my local laptop. If you're working on Linux, there is a command called nproc, and there are different ones for Windows and Mac, but I can't go into all of them, unfortunately. And this will just tell you, for example, the number of logical processes that you have. So in this instance, I've got 8. I think if I put nproc in without any arguments, 8. You can also look at, in Linux, the CPU information is also stored in a file called /proc/CPU info. In this instance, it gives you a lot more information about the machine. So here we can see we've got sort of printing off information for each logical core. So this is logical core 6 and logical core 7 because we start indexing from 0. So logical core 0 here. So that's also looking at all of the 8 logical cores. Another way you can find out information is to just look up the model of your CPU, and Intel will have a data sheet about the particular CPU that you're using and any specific information that might help you understand what the makeup of that CPU is. So let's go back to the login node. So go back to the login node, sort of clear this up. We can use the same techniques to look at things on the login node. So let's look at proc CPU info. So in this instance, you can see that we've got AMD processors, not Intel processors here. And there are, we do nproc 256 CPU, not CPUs, cores. We can learn a little bit about the memory on the node by looking at meminfo. So this is another location where you can go to find data. And you can kind of Google, like, how do I find the amount of memory on my Linux machine? And there will be sort of articles that sort of explain how to do this. Here you can see we've got basically 500 and, what's that? So that's bytes, megabytes, so 527 odd gigabytes of memory. And then this is the amount available, so we're currently using about half. If we want to know about disk storage, there is a command called df, and just to make it readable, we can put a /th here. So there's a lot of attached storage here for temporary systems. There's quite a lot. It's there. Oh yeah, here we go. So now we're getting back up to some of the important storage. There's a good one. There's home. So home here, for example, you can see we've got multiple hundreds of terabytes of storage available, and then work was attached to. I'm going to use a command here. Remember grep from yesterday? You can use that to try and find work. So you can see worked, which has multiple kind of storages here, has got 3.3 petabytes of storage. So an inordinate amount of storage compared to what you have in your usual laptop. Final thing you can do is in the command line, there are some useful monitoring tools which give you live information about what's going on in the system. The most common one people use is just called top. And this will print off a bit of information about what processes are running. This is kind of like task manager in the shell. How much CPU usage is occurring, how much memory usage. And so forth. And if you press H in here as well, you can get some commands for filtering or highlighting or sorting on particular things that you might be interested in. But we'll get out of that for now, so just press Q if you want to exit that. All right, the next exercise sort of talked about looking at a particular node. So we can't log into a node just to look at its information, but we can ask the scheduler, Slurm, for a little bit of information about a particular node. So in this instance, we're giving the node name that we want to get some information on. This is node ID 1053, and we're just going to specify a more readable format here for output. So in this instance, we're getting the node name, the number of CPUs, and the amount of memory. So this node has 256 CPUs and 227 gigabytes of memory. If we look at one of these high memory nodes, so I just used sinfo there to find one of the node numbers. Let's look at 002784, for example. We can see this node has also 256 CPUs, but about double, 456 gigabytes of memory. Okay, so I've got another question in the chat. All right, so thanks, Robert. Robert's pasted some ways to get information about your system in the shell on a Mac in the chat. So thanks for that. Are there any kind of questions about nodes or the makeup of high-performance computing systems, or anything else that comes to mind that you might want to know about HPC systems and the architecture and makeup of them before we move on to talking about the scheduler in the next section? All right. Let's move on then. This is the last section before lunch. I'm hoping we can get through this. We should, or maybe we'll get up to just before the exercises. That should take us up to about 12. And then we'll take, again, maybe about an hour for lunch so that we don't go beyond 4 p.m. this afternoon and still manage to get through most of the content. All right, working with the scheduler. So the next session is going to be all about Slurm, which is the job scheduler on ARCHER2, but all schedulers work relatively similar in the sense that they perform a task that is to distribute the workload and to monitor the workload of many users across the whole high-performance system. We're going to try and answer a few questions in the session, as in what is a scheduler and why they're used. And then we'll do some exercises where we learn how to launch a program using the scheduler and how to get the output back from that. So I didn't come up with this analogy, but it's pretty apt when it comes to a scheduler. You can kind of think of a high-performance system as a restaurant with a number of tables, and each seat is sort of like a node or a core, and there can be many kind of users queuing up at the front, and they need to essentially be seated in particular arrangements. So some jobs might need to be together at a table. Some jobs might need to be, or some diners might need to be, or could be at any table. They might not necessarily need to sit together, even though they came to the diner together. And the restaurant has a certain makeup. It has a certain number of tables and a certain number of chairs, and it may have like different floors. And it is the scheduler's job, essentially this queue manager here, to decide where and when the different diners in the queue get to sit and eat their meals. The meals obviously being the compute resources that they wish to consume. So that can be quite a difficult task because not every job that or every diner that comes to the queue manager is the same. They all have different requirements. So they might want to sit at the table for a different amount of time. They might need more or less space within the restaurant. And the queue manager looks at all of these things, as well as managing the different restrictions that might be placed on the different diners that are coming. So those restrictions, for example, are the maximum run time, so how long you can run or sit at the table for, how much resources any one individual job is allowed to consume. So maybe one diner's come and said, I need 1,000 seats in the restaurant, and the queue manager says, well, the maximum you're allowed is 500, so that diner might get turned away. It may even refer to the types of tables that particular diners are allowed to sit at. So some diners may be allowed access to standard tables, and other diners may be allowed access to high memory tables. So the queue manager has a very important role in the sense that it makes sure that jobs are distributed in line with the restrictions that are placed on the person that submitted the job. And it makes sure that jobs are executed as efficiently as possible. So to give you an example, let's say there's 2 jobs in a queue. One needs 50 cores and another one needs 20 cores, and there are only 25 cores available. In that instance, the queue manager may decide to allow the 20-core job to go first, even though it came after the 50-core job, because it knows that somewhere else in the restaurant, 50 cores will become available not too far in the distant future. So it will prioritize jobs that can run. It may be even that jobs which only want to run for a short amount of time will get priority because they will be in and out of the queue relatively quickly, allowing longer term jobs to then consume resources. There's lots of different algorithms that system managers can use to work out how these queues should kind of be optimized. Each system administrator may just use the default that comes with their scheduler or kind of tweak it a little bit to their own needs. So generally when you start submitting jobs, you'll kind of get a feel after a time for how the queue manager will treat your job submissions based on what your requested runtime is, what your size of your job is in terms of the number of cores you want, and so forth. So ARCHER2 uses Slurm. We've kind of talked about this, and although Slurm isn't used everywhere, the style in which you interact with and send jobs to all of the different scheduling software is pretty similar, although the exact syntax we're going to use today to submit these jobs and the names of the commands may be different. Does anyone have any questions about the schedulers and the restaurant analogy? Maybe you might be thinking about how this applies to the type of work that you think you'll be submitting to your cluster when you get around to it, or have already submitted. Okay. All right, so we're going to start by running what's called a batch job. If everyone can log back into ARCHER2, if you haven't already, I'm just going to go back to my user directory, and cannot remember. Yeah, I think you can do it from your user directory. There'll be something later where sometimes if you're trying to do stuff on ARCHER2, data that the nodes require is only available to them from the work directory path, which we'll move to at some point. But for just submitting simple jobs, you can do that from your home directory, which isn't exposed to the worker nodes. So we're going to start by using Nano to create a shell script called example-job.shell. And in that script, we're going to shebang bin bash. I'm just going to do something really simple. We're just going to echo the script is running on, and then get the host name. So this will be, remember, host name gives us the name of the computer that we're currently logged into. I'm going to save that by doing Control-O, Enter, Control-X. I have to change the permission so I can execute it. Right. And then if I just run that locally, then I should just get this script is running on and the name of the login node that I'm logged into. Cool. So that's all good. Now to submit this job to a worker node rather than just running it on the login node, we can use the command batch. So this is for running batch jobs. If you think back to our examples of different types of workload right at the beginning, a good example of a batch job would be the guy who was running many embarrassingly parallel problems. We have to tell the scheduler a few things. The first is which partition we're going to use. We're just going to use the standard partition. Remember, this refers to the type of machine we want, so we just want a standard machine. We also have to specify the quality of service, and for ARCHER2, that's usually just short, because we're just running a short job here. And then we can give it the name of the script that we want to run, or the executable that we want to run. Now, if we try to do that, we're going to get a little bit of a warning because we didn't tell the scheduler how long we thought this job would run for. So they've just set it for the maximum time of the short queue. So short queues are just 20 minutes. So they've just set time to be the maximum length of the short queue, which is 20 minutes. We also get a warning about not being on the work file system, which I sort of mentioned earlier, and we'll address that by moving to work when we actually need to load some data onto the nodes. Either way, our job's been submitted, and we get a reference number back telling us what the number of the job was. If I then run list, I would have expected some output from this job that talked about, or that had the reference number in it. And the reason I haven't got anything back, even though the job ran, was that the nodes themselves can't talk to this particular file systems. They can't talk to this, so the worker nodes can't talk to this home file system. So to rectify that, we need to move to what the warning here called the working directory. And the working directory is at the root file system, so /work, and then it's the same as your home directory after that. So everyone should be able to move to /work, TA076, TA076, and then your username. And in here, you won't have any files or folders yet. I've got one called testing because I was doing some stuff the other day, but this is a completely separate area to your home directory, and it's that sort of scratch area that we talked about yesterday for working on your data. To move the example script that we just ran to this area, we're going to have to use the copy command, and it's just in our home directory, so we can use the tilde, and then we can copy the example job script across to this location. Oops, sorry, need to copy it to this location, so we're just going to put a dot here. And then list the contents of the folder again. You can see that the script is here. So let's try to submit our job again. Remember, you can use the up arrows to get the same command. And I'm also going to put a time on the job. This job won't take very long, so and the time here is just in minutes. I'm just going to put a 1 there to remove any errors we might get on output. And the job is successfully submitted with a batch job number of 2095120. So you can see that's a slightly higher number than what was there before. That's because another 15 jobs got submitted between my previous one and this one. Probably most of those were you guys, but that's okay. I then clear this and list the contents of my current directory. You can see that I now have a .out file with that job number in the name. And we can have a look in that file. This is another command I sometimes use called more, sort of similar to less, but it just outputs as much as it can. And we can see that the out file captures the output of the script that we submitted, and it tells us that the script was run on the worker node 6288. And all of you might have slightly different numbers here that tell you where the scheduler essentially sat you in the cluster restaurant. Another useful command that the scheduler has is it can tell you a little bit about where you are in the queue. And to do that, you use the sq command. And the -u option here filters or allows you to filter the output to your particular user or any other user for that matter. And you just want to put your user ID in here. So your user ID again is the name out the front here, or the output of the who am I command. In this instance, I don't have any active jobs, so my queue is empty. What I could do here is quickly resubmit this job and then look at the queue again. And you can see that now there is an object or a new line in the queue which references the job that I just submitted. If I look at the SQ again, the job will disappear. And that's because the job completed and I've now got an output file. And if we compare these two output files, A, B, we can see that I ended up running on the same node both times. There is another useful command that you might use occasionally when you want to keep an eye on a queue, and that is the watch command. Watch takes as its argument a refresh time, so this is how often it will update itself or how often it will recall the command that you ask it to. So in this case, let's say every 5 seconds, but you know, if you've got a long-running job, every 20 seconds or even every 60 seconds might be sufficient. And as arguments, it takes the command that you want to watch. So in this case, sq-u and username. And this will essentially refresh the view every 5 seconds. So we should see this tick over. So this number up here in the top right, tick over every 5 seconds as the output is updated. So this could be useful if you're watching like a large number of jobs, or if you want to know whether your job has been submitted or not. And you don't want to have to call sq-u username every 10 seconds manually. And to exit that, you use Control-C, just the interrupt command. Let's see what happens if we, again, submit our example job. Now watch the queue. The moment the job is there, now we can see that the state has changed and it's running. We can also see which node it got allocated to, so it ended up on a different node this time, and that represents completion of the job because it's dropped out of the queue. URLs, and we do our cat comparison again. Let's do 46.out. Now we have the 3 times I've run this script, and the last time that it ran it, we can see that it was on node 3074, which matched what we saw in the watch command. So in all these cases, we've kind of just used the default options of the scheduler. So it has like some sensible defaults in terms of how much resources that it allocates to us, but that may not always be appropriate. We may want to ask for many nodes or many CPUs. We may want to ask for CPUs limited to a single node. We may want to ask for GPU resources or the high memory nodes. And so in those instances, you need to pass additional flags and values to the job submissions that you're doing. Now, it can be a little bit tedious to type those in on the command line all the time. So it turns out you can actually put them into your job script. And the way you do that is starting a line with a comment right at the top of the file, below the shebang, and then putting in capital letters sbatch. This is for Slurm, but other schedulers will be similar with their own kind of keywords here. You can then add options after this sbatch. So a common option might be job name, and we could, I'm just going to call this Tony's example here. And an example that we're following, add another another line below here. Write that out, enter, exit. So now if I submit that job again, and we watch the queue, you can see that the job now has a name, although it's abbreviated here or shortened to fit within the table. All of the command line arguments that we're passing to sbatch can be put into the script. And in fact, if you do sbatch help, you can see the large number of arguments that sbatch is capable of taking. And you don't need all of these, but there will be some common ones that you come across as you start to submit jobs, which suit your particular needs. So let's move our other arguments into our job script. We'll create another SBatch line here. Paste these in. And you can put these on the same line, but I like to kind of spread them out over multiple lines because it's a bit easier to read and you can add or remove them as you need. So what this means is instead of writing a command like this, we can just submit the job script and those arguments should be carried across or interpreted by SBatch. For Alice here, so that was 5165. And we can see that that all ran okay. All right, any questions there about SBatch or adding arguments to the job scripts or I don't know, any of the details we just covered in the last few minutes? So the name standard will depend on the cluster that you're running on, but essentially if you run sinfo, you can see here the partition at the top, and this is where different kind of nodes have been allocated to a particular partition. Think of it as like having, you know, like different levels in the restaurant. So different types of tables might exist on different levels. You might have like the high volume rooms on one level, which is a partition, and the normal volume tables on a different level. The names are somewhat arbitrary and dependent on how a particular administrator has set up their cluster. Exactly, yeah. Thanks, Kevin. So, you know, ARCHER2 has its documentation, which I'll just post in the chat. You all would have used this to set up your quick start. Let's see, to set up your SSH keys and your access. But hopefully any system that you connect to will have something similar, and you can kind of search partitions here, search bar, and it will tell you a little bit about what all the different partitions are and how they're organized. So here you can see they give you the maximum number of nodes, each of those partitions, and the makeup of the systems in those. They also give you some information here about the quality of service. So you can ask for different qualities of service, and they have different restrictions in terms of the sizes of the jobs you can run, how long the jobs can run for, and how many simultaneous jobs can be queued or run at any given time.
So my question, which what happens if your time limit is too short?
Okay, so if your time limit is too short, then you will lose all your work. There are a couple of options here, and the main thing that a system administrator would tell you is that you need to save interim results as you go and have the capacity to restart your work. So you should be designing or using algorithms that can be restarted if something happens to the system based on the saving of sort of chaptered or like checkpointed results. In CFD world, that would mean that you might want to save the state of your simulation every 30 minutes to an hour, say. And then I think most CFD software would support restarting the job from the most recent state of the system. Yeah, so if your software is saving results as it goes, you will see them. But if your software or the program that you're running only dumps results at the end when it's completed its job, then that information won't be saved out. You will see any output to the terminal from your job running in the .out file. Cool. Any more kind of questions like that? That's a good one. Other things that might cause your jobs to be killed early: if you launch a process which consumes more resources than it's been allocated. So let's say you run a program that automatically detects how many cores are on a system, and it starts consuming as many cores as it can when you've only asked for 10, then the scheduler will boot your job from the system. The same goes if you're consuming more memory than you've been allocated. The scheduler will decide that you're not playing fair on the system and kick your job. So you need to essentially, yeah. So that's another good question. So understanding how much time your job's going to take will depend on a bit of heuristic feedback, where you will learn from running the job in particular configurations how long it takes, and then be able to parameterize it effectively to either run it within the allocated wall time or to restart it automatically when the job finishes or hits the wall time, so that you can essentially checkpoint the job, save the interim results so that you're not having to rerun things all the time, and then continue from that checkpointed kind of state. You can do a little bit of benchmarking, I think, to try and understand how your jobs might perform, either locally on your laptop or maybe with really short runs on the nodes, the login nodes. No, you don't get told off if you request more time. The way that will affect your ability to run jobs is if you request the maximum wall time and your job finishes early, then the scheduler just accepts that, and that's totally fine. But your jobs will take much longer to start if you have the maximum wall time, because the availability of a table will be significantly limited compared to if you request a wall time much closer to what you actually need. So the shorter your job is, the higher up in the priority queue it will go, because it's easier to find space for your job in the available resources. You also don't get charged if you request more wall time than you actually used. You only ever get charged usually for the wall time that you end up running your job for. All good questions. Does anyone else have any other kind of questions about the scheduler and how that relates to your use of resources? This is the previous lesson. All right, so there are a few other flags that are useful to know about with Slurm, or any of the schedulers for that matter. The first one is -- nodes. So this is how many nodes you think your job might need to use. Obviously, if you need more than 256 cores, then you're going to need more than a single node. This is the number of parallel processes per node that you want to run. So this is, how do I describe this? It's like the number of jobs that you might dispatch on a particular node. So let's say you have three jobs that you want to dispatch, and each one of those needs a single CPU, then you can manage that through this flag. But if you need more than one CPU per task, so sometimes you'll have tasks that are themselves able to run in a parallel sense, and then you need to have multiple CPUs per task. You can specify that with this option. The way that you request resources will depend on the style of or the characteristics of the problem that you're trying to solve, and the capabilities of the software that you're using. So some software might be written in a purely tasks type space. Other software might be written in a tasks and CPUs type space. And you'll get to know what the most appropriate approach is for you by working with your system administrator and the help desk, or talking to people that are already using the software that you're trying to use. The last one here we've already seen, and this is the wall time. So this is the real world time that you require to run your job, not just the compute time. And there's obviously an upper limit to what this can be depending on the quality of service that you request on Archer. This is an important note. So if you have a program that only runs in serial, you can request a large amount of resources and you'll be charged for a large amount of resources, but it won't necessarily mean that your program runs faster. You need to understand how your program runs and how it uses the resources so that you can match the resources you request to the capability of your software. you can't simply throw more cores at a problem that doesn't know how to use those cores, essentially. We talked about this already. You can mix and match command line options or job script options. If you write a job script and it has the options in the job script, it will use them. If you specify them on the command line and still call the job script, then the command line options will override whatever you had in the job script. So you can quickly replace defaults, say, in your job script if you need to. All right, we've got a couple of exercises here before lunch. The first one here is to modify the example job script we wrote, the example-job.sh, so that it sleeps for a period of time, and then see what happens if you specify a time that is above or below. So this is sort of going to test what happens if we don't specify a wall time for our job. So in this instance, we're specifying 30 seconds for a job that needs to run for 120. So you'll kind of see an example of what happens when you don't allocate enough time for your job to complete. So I'm going to post this exercise here in the chat. Hopefully this doesn't take too long to run through this example, and then we'll come back at 10 to 12, quickly run through this example and break for lunch before doing the rest of this section. Just in the meantime, if you have any other questions, feel free to drop them in the chat or send me a message, and I'll do my best to answer them. Okay, so it's now 10 to 12. I just want to run through these examples or these exercises with you quickly, and then we'll take a break for lunch. Just got a poll up at the moment. I think if we take the scheduled 2-hour lunch, we haven't quite made it to where we need to be. So hopefully an hour is a sufficient break for everyone, and we can kick on again at 1 p.m. after we break. So if we go back to our exercises, the first one here asked us to put everything that was a command line flag into the job script itself. So I already did that for you guys. So now look at what's in our example job. We can see that we've added all our flag options here as batch comments. So that's all good. But it also asks us to get the script to run for a minute. So to do that, we need to use a new command that we haven't seen before called sleep. It essentially just tells the shell to wait for a certain amount of time, in this case seconds. So this is the number of seconds that the shell will wait before moving on to the next line of the script. And we're only running here for 1 minute. So if we want to run this for a little bit longer, then we'll need to give it a few extra seconds. We can do that by specifying 1 minute and 15 seconds, for example. And if we need to save this out, so Control O, Enter, Control X, and I can submit this job now. Just write it down, dispatch, and we can watch job, and it should take roughly until core 53:45 essentially to complete. We can see that the time that the script is running for is ticking over here. So that's 38 seconds, almost there. .53 seconds, and the job should almost complete. So job sending now, and the job's done. So we go have a look at the output of the job script, which was 282. You can see that it just shows us the output as we expect. In the shell environment, you also have what are called environment variables. And these are variables or global variables that exist within the shell environment for all scripts or jobs or executables to use. And Slurm does some things where it injects a few environment variables into the shell that it starts on the worker nodes at the start of each job. One of those is an environment variable called Slurm CPUs per task. So this kind of tells us about what we requested from the scheduler. And this can be a useful way to essentially communicate information that you tell the scheduler to perhaps scripts that you're running or programs that you're running from within script. In this instance, we need to echo that variable, and it's a variable, so we need to put a $, in front of it. And I'm just going to actually put some extra information in here, a bit more readable. We're going to put some braces to have that exposed properly. I'm just going to reduce the sleep time here so we don't have to wait so long for this to run. And then the other thing we need to do is specify this option, and the option was CPUs per task equals, and let's just ask for 4, say. Write that out, exit. Let's just check that this all works. Wait 5 seconds. So we haven't got that environment variable on the login node, so I won't be able to print that. But we can see that the job script is working. So let's submit our job. Submit it OK. And then we should be able to see the output of that job, 299. We can see that the CPUs requested was 4. Right, what's next? In the instance where, let's edit our job again. Let's say that our wall time here is, and request is 10 seconds. We're going to make the sleep time 20 seconds. If I submit that job now, we're asking, or we expect our job to run longer than the amount of time we've requested from the scheduler. So in that instance, we will see what happens. Remember, we only requested 10 seconds worth of job time. So the status should change here pretty soon. So that job's shutting down. Not sure if this worked or not. There might be a little bit of leeway on this because it takes some time for the scheduler to know that you've overrun your time. The queue manager is a busy worker and he's looking at a lot of jobs. He doesn't always necessarily come to check on you instantaneously when you 355. So that job finished successfully. So we might have to extend the sleep to be a little bit longer.
20 seconds grace.
Oh, you get 20 seconds grace. Okay. Well, let's ask for 5 seconds here. See what happens if we go over by 20 seconds. See the job. Watch the paint dry for a little bit. So we only requested 5 seconds of wall time this time. So when we get to 25 seconds, hopefully the job will be interrupted by the scheduler. No, still running. It's too much grace these days. There's a lot more. Might have to consult with the ARCHER2 team to find out how long I need to run for before I get cancelled. All right, I don't think that's worked. Either way, if you do come up against the wall time of your job, you will probably get an error like this printed at the end of the out file. And this will tell you that essentially the scheduler forced a kill on your processes because you ran into your requested time limit. If you overuse other resources like the number of CPUs or the amount of memory you've requested, you might also see similar errors printed at the end of your output where the scheduler has protected the system by preventing you from overusing your allocation or using more than your allocation. And the reason it does this is primarily to make sure you don't ruin the experience of using the cluster for other users and other jobs that might be sharing the same node as you. All right, let's leave it there. It's 12 o'clock. I'm going to come back in an hour, so 1 p.m. British summertime, and we'll continue with the rest of the section. Enjoy your lunch. Again, any questions, just drop them in the chat, and I'll do my best to answer them. And I'll see you all soon.